Great. Hi there. Welcome to everyone. It's great to be here this morning. It's fun to see a whole room of people who care about Great Salt Lake. I don't have Rob's nice Scottish brogue, so you're going to have to go back to a normal Western U.S. accent and bear with me. Okay, today I'm going to be talking about Great Salt Lake hydrology. I am a professor of watershed sciences at Utah State University. I'm a kind of a hydrologist or physical geographer, really broadly. I do systems analysis, and in particular, I focus on environmental water management. So how could we improve water management to some natural places and maintain human water uses at the same time? That's kind of the goal of all my research. So we're going to be looking at the problems of Great Salt Lake today through a hydrologic lens and really thinking about the hydrology of the Great Salt Lake and what that can tell us. Okay, so as we all know, Great Salt Lake declined to a historic low last year in 2022. This graph is showing through time, starting just after 1900, showing Great Salt Lake, the average annual lake level every year. So we could see that in the late 1980s, we had those really high lake levels. That's when the pumps were working and we were pumping water into the West Desert. Then in the mid-90s, we kind of had a middle elevation that was pretty good. And then now we're at this very low place, kind of reaching its lowest point last fall. Since then, we've had a pretty nice wet season, and I'll talk more about that. But you can see that from the late 1980s until now, we've had this really steady downward trend. You know, you can't really say, oh, that's just variability. Like, we are just in a declining trend. And we all know that lake elevation matters to all of us. First of all, it matters to the ecology of the lake. And the ecology of the lake, you know, we have birds that migrate throughout the northern and southern hemisphere. So the ecology of the lake really has kind of a global importance. So these figures here, these arrows, those are adapted from forestry, fire, and state lands, traffic light signal, where green are showing good elevations or suitable elevations, and the red areas are starting to show where we get into problems. So what we should take from this is there's no single elevation that's going to meet all the objectives or be optimal for every single objective. However, there are ranges that we should be at. So kind of, you know, I think around 4,200, give or take a little bit, 4,200 feet. That seems to be the best for most elevations. So moving from left to right on this, we have, you know, the first one is the salinity, including things like microbialites, the brine shrimp, the brine flies. We want more of, you know, around 4,200 in there. Moving into the bay habitats and bacteria on the second column. The north arm bacterial diversity in the middle column there, moving into wetlands, and then ending with dust. Dust, as Kevin mentioned, you know, the higher the lake elevation is the best for dust. But even aside from the ecology, Great Salt Lake matters to all of us. It matters to our state economy, where the lake directly generates over $1.5 billion in 2023 dollars. Matters for air quality, and because of that, it affects our human health. And Kevin did a really nice job of discussing that all for us this morning. So we know we care about Great Salt Lake. So what I'm going to talk about today is what is the hydrology of the Great Salt Lake? Let's go over it so we all understand it. Why is Great Salt Lake level so low? Will a wet year save us? And then what are some promising strategies to preserve Great Salt Lake? And my first degree, my bachelor's degree, is in economics, so I still dabble in economics, and I tend to tie a lot of my work into economics so that it's really intuitive for everybody to understand. So by the end of my presentation, you'll see me do some of that. So as a reminder, Great Salt Lake is always undergoing change, right? Great Salt Lake is the remnant of Lake Bonneville during the Pleistocene. We know that the lake has had many different levels, and I always like this slide, or put a slide like this, so that we remember that Great Salt Lake is always changing. And some of those changes are outside of our control, but some are within our control, and that's going to be the focus that I talk about today. So now we're going to get into the hydrology itself here. So of the water that gets to Great Salt Lake, streamflow is really a biggie. Streamflow contributes about 2/3 of the water to Great Salt Lake. Direct precipitation, so that's precipitation falling directly on the lake, is about 31%. Groundwater is maybe 2 to 3%. And of these terms, groundwater is where we have the most uncertainty. These figures here are dating back to studies done in the 70s. There are a number of groups undergoing research on groundwater right now. So this is an area of active research, is trying to pin down exactly the contribution of groundwater and how it might change through years. But going back to the streamflow, so streamflow is 2/3 of the water that gets to Great Salt Lake. And of the main rivers that all flow in from the Wasatch Front, Bear River is the biggie. It contributes over half of that amount of streamflow. Weber and Jordan then make up kind of almost the rest. There's slight contributions from some drains and from the West Desert, but those tend to be pretty small and sometimes ephemeral. One thing to also notice in this figure is that all of the rivers from the Wasatch Front feed into the south arm of the lake. So Bear River goes into Bear River Bay, Weber and Jordan go into Farmington Bay. So all of that fresh water is coming into the south arm of the lake. When I talk about arms, that becomes important because we've constructed a causeway, a solid fill causeway that bisects the lake. So now I think of the lake as really having two distinct portions of the lake. The north arm, this figure here is facing west, so the north arm is the reddish arm. It can be up to 27% salinity, so it can reach saturation. Then the south arm, shown more in the green here, last fall, that reached 18% salinity. And that's really a problem because that's the threshold of where some species can exist. So things like brine shrimp and brine flies, they were at their tolerance levels. And so that's a problem for the whole ecology of the lake and for our resilience of the lake. So now let's think about the water balance of the lake. And this is something hydrologists do to understand basically where we can make changes and where we can have the most impacts. Terminal lakes are really nice because they're kind of blissfully simple. When you think about big water supply systems in cities, and terminal lakes are really nice and simple. So thinking about how much water is in the lake, if we want to change the volume of the lake, we have a couple terms to keep in mind. The first is stream flow. So as I've already mentioned, 2/3 of the water to the lake comes from stream flow. That's the Q term. Plus groundwater, we know that groundwater is pretty small. Then we have precipitation times the area of the lake minus evaporation times the area of the lake. And then here we have diversions. Most terminal lakes you wouldn't have diversions, but here we do. Because we can have West Desert pumping, which removes water, or because of mineral extractions that take water from the lake and it evaporates, so that water never comes back to the lake. So in this case, we have some diversions. So if we want Great Salt Lake to increase, we know that we need to increase either stream flow, groundwater, which is small, or precipitation. We don't have a whole lot of control over precipitation, but we do over stream flow because of our diversions and our human uses, and I'll talk more about that in a bit. And then if the lake is continuing to decline, like it has been in the last, say, 25 years, that means that the evaporation term has been outweighing the other terms. It's been larger than those other terms, so the lake has declined. So one of the strategies that we've done recently and we're doing more of is changing the area of the lake. So we have in the causeway that bisects the lake, there's a breach shown on the left figure here. So the breach is an opening where some water can pass through so that some of the salinity and some of the water can pass between the north and the south arm. The hydrodynamics of it are pretty complex, but we're increasing the berm. So we're raising the berm. In the right figure, you can see where there's a berm underneath the surface of the water, and we can raise that or lower that. That's one of the ways that we can adaptively manage the lake. The berm was constructed to have this sort of adaptive capacity, and we're using it right now. So we're increasing the berm basically to separate the north arm off. So separate it off and keep all those salts on the north arm, where then all the fresh water is going to come into the south arm. So by doing that, we're changing the area in this water balance equation. And here I've also put the salt concentration. So the salt concentration is the salt load coming in each year. So we think of streams as being freshwater, and they are, but they have trace amounts of salts and minerals, and there's no way for those to leave except, well, through mineral extraction, but naturally there's no way for them to leave. Only the fresh water evaporates. So the salt load minus the volume. So right now we're changing this lake. And this is kind of what I think of as an RLC solution. This is what a RLC did. They changed the area of the lake in order to manage it. All right, so now I'm kind of edging it on Rob's turf a little bit, and I'm showing the mean precipitation anomaly. This is for the whole state of Utah, so this is averaged over the whole state. This is from 1900 to present. And then the black line is a 10-year mean going through here. So when I look at this, I'd say, you know, I don't see huge changes so far to precipitation. That doesn't mean they're not going to happen in the future because of climate variability, but so far I haven't seen big, huge changes. We'll talk about the kind of the most recent 20 years. We're going to come back to those in a little bit later in the talk. And then this is mean temperature anomaly for air temperature. And again, I should have explained these figures a little bit better. So everything in red is warmer than normal in this case, and everything in the blue is a little bit cooler than normal. So you can see that we're having this shift. We're getting warmer temperatures here. All in all, that leads to some drying. Rob did a really nice job of discussing that. We know there's some periodicity to the lake where the conditions of the lake tend to lag what we see in the climate by maybe, you know, 8 to 12 years, in that ballpark somewhere. All right, so now let's look at unregulated flow. So unregulated flow is also sometimes called natural flow. This is modeled. So natural flow is modeled. So we use models to say, if there were no diversions and no human water uses and no land use changes, what would be the stream flow? So we make a water balance and we can estimate what natural flow would be. This is really useful because it separates out diversions in human and consumptive human water uses. So earlier today, Kevin showed some figures that include diversions, and so we saw stream flows that had this strong declining trend. But if we look at just natural flows, what the flows would be like without any people on the landscape, we can see that these are pretty consistent. So what stands out to me is I see a lot of year-to-year variability. I see wet years, I see dry years, so I see a lot of ups and downs, but I don't see a trend. I don't see a declining trend or even an increasing trend. I see pretty uniform average flows. So even though we know that the climate has warmed some, we're not seeing big changes on our unregulated flows. By the way, and importantly, this data goes back to 1989. So this is the last, say, 30 years, close to 30 years, 25 years or so of data. All right, now let's look at consumptive water uses here. So consumptive water uses, so this is the water that we consume, very much like the term describes. So it is evaporated, transpirated, we might drink glasses of water, use it for cooking. It's water that's consumed and will never return to the lake. And this is really different to separate this from diversions, because we can divert a lot of water, but some of that might actually return to the lake, right? Some might flow through interflow or groundwater or runoff and come back to streams or come back to the lake. This is water that's consumed. It will never come back to the lake. So here we can break this up by uses. So in the black line, I have total consumptive uses. Then we see agriculture, municipal and industrial in red, managed wetlands in orange, mineral extraction, and reservoir evaporation. Another thing that sticks out to me is these are all pretty consistent, right? So we go, okay, well, we have pretty consistent stream flows so far. We have pretty consistent human consumption. The one thing to note is that human consumption is really high. Compared to our stream flows, we're using anywhere from 50% to maybe 66% or so of our stream flows we're consumptively using. So we're using a lot of this water, and in doing so, we've taken a good deal of the resilience away from the lake, that resilient capacity. But there's a little bit more to the story. If we go back farther, we know that we developed our water, we started giving out, we started managing water rights, developed our legal code, our water code here in the mid-1800s. And so that's when we started not only diverting water, but consuming water. And so this top figure is showing Water uses through time, consumptive water uses through time. Agriculture really jumps out, but there are other ones also, right? There's urban and municipal, there's mineral ponds, there's managed wetlands. And so the bottom line that I like to think of is we're all using this water. All of Utahns, we're all using this water. And then the bottom figure is nice. It shows the red line is our measured lake level. You see a little bit of, variability year to year and even seasonally. And the green line is modeled data showing what we think lake level would be if we had no human consumption. No consumptive uses. So agriculture, cities, all of those changes we've made, we would expect to see a lot of variability in the lake, but not this downward trend. So this tells us a lot that human consumption or consumptive water uses are really a major knob that we can turn. It's a management knob. We also know that our infrastructure dates back over 100 years. So this figure on the left is showing reservoir capacity. This is just in the Bear, Weber, and Jordan basins. So beginning about the 1900s and continuing into the beginning of maybe the 1950s, 1960s, we started building a lot of reservoirs. That changes water flows a lot. That changes management of the water reaching the lake. And of course, we build reservoirs because they help us. We want to have lots of water in the summer, which is our dry season, and have those nice steady flows for irrigations for cities and take off the floods. Rob mentioned a lot of the flooding. Try to take off those flood peaks and store water for the summer. So it changes our flows considerably. But again, there's some promise in this. There's some hard decisions, but there's some promise also in that consumptive water uses are policy level. This is something that we can change. When we think about climate change, there are things we can change, but it's probably hard to do on the scale of Utah. But when we think about consumptive water uses, that is something that we can change on the scale of Utah. All right, now, a bunch of you in the audience might be thinking, okay, yeah, but this is a wet year. So is this year going to save us, or do we still need to be concerned because this is such a gangbusters year? This is the year we've all been waiting for. So here I've taken plots of snow water equivalent. Rob did a really nice job of explaining those. So we can see percentiles. So the blue area is showing our wettest years. The red is showing our driest years. The median line is in green there, and the median kind of high peak area, peak flows, or peak snow water equivalent is in green. This is through 1 year, it's through one water year. And then in black, we have this year. So you can see we're doing great, right? We're starting to get up into that blue area. By the way, this is just for the Bear River Basin. It's not for the whole state. So we're looking good so far. It's only the middle of March, but we're looking great. So let's compare this now to a couple of other really wet years. So here's 2017, another wet year. We're tracking a little bit later maybe. 2011, we're pretty right on track to where 2011 was. 2011 was noticeable in that snow water equivalent peaked pretty late, peaked about May 1st. That's a little bit late than is more typical. 1997, that's where we were looking. We had more earlier snowpack in 1997. But so we can look at these previous years, previous wet years, to say what happened to Great Salt Lake in these years. And that gives us a really nice way to understand what might happen this year without having to do a whole lot of modeling, just using the data that we have. So this is a figure showing through time the annual elevation change of Great Salt Lake. So you can see 0, that's showing no change in lake elevation from year to year. And you can see some years when the lake increased its elevation and some years that the lake dropped. Lots of years, in fact, that the lake dropped. So what I want to point out to you is, I don't know if this pointer, after Rob, there we go, it works. So here we have 2011. I'll try to keep talking to the microphone. We have 2011, so this was a wet year. Notice that the lake increased by about 2 feet in elevation. So that what this tells me is we can't bank on a single wet year to get us there. We're going to need to do more than just wait for single wet years. 2005, right in here, about 1/2 foot elevation. So this is annual average. So this is once we go through the summer when evaporation tends to increase. Overall, we might, maybe we'll have 2 feet of elevation. Maybe it'll be a little bit more. Remember that we have bermed, we have raised the berm in the causeway, so this is going to change the area. So this year is a little bit more of an unknown, and we're continuing to do that. But we probably can't just bank on a single wet year to save the lake. One more caveat is that 1 foot of water or 1 foot of elevation gain can require different volumes of water because the lake is a basin. It's kind of this shallow bowl-shaped. So a foot elevation at a very low lake level will require less water than a foot increase at a higher elevation, right? So just one reminder, we always talk about a foot elevation, but they can require different amounts of water depending on where we're at. Just remember that. And then also we have some competition for this wet year water. So these figures are showing on the right here, I have the teacup diagram for the Bureau reservoirs. And so this is showing how full they are. This is taken, I think, Monday I took this plot. I don't know what's up with Willard Bay. There's clearly water in Willard Bay. Maybe that data wasn't working from the Bureau. But so we want to go into irrigation season and into the summer with full reservoirs, right? So that's our goal as water managers are going to be trying to not have flooding. This is a tricky period as we get into spring and warming and lots of snowpack. We want to not have flooding, but end the snowy season with full reservoirs. And then this plot on the left is really telling. So this is kind of a runoff year. So it starts in April and it shows the reservoir storage for the whole state except for Flaming Gorge and Lake Powell. Those really big ones that behave a little bit different. So you can see the mean capacity, the mean reservoir capacity where we kind of normally are, much higher than where we have been in the last 2 years. And then when we can see the previous year in blue here, we started off in good shape, and then we had a warm summer, a not very great winter, and we ended the year not, out in this range, not nearly as high reservoir storage as we wanted to be. So this year we started really low. This green line right over there started really low, and now we have a pretty steep curve. So we're raising that. We're trying to fill our reservoirs. But because of that, all of this water that is up in the snowpack is not going to reach the lake. A lot of it we're going to use for our other water objectives. One more reminder, so the U.S. Drought Monitor still has large proportions of Utah in drought. Northern Utah, where we are, isn't a severe drought, and that's because of things like reservoir storage and overall dry conditions, dry soils, things like that have taken a good deal of water just to kind of get back to normal, get back out of these drought conditions. All right, so let's come back to this precipitation anomaly figure that I've shown, and let's focus on these last 20 years where the whole West, the American West, has been in a prolonged and ongoing drought. So a couple things really jump out at me from them. First, we've had longer droughts, right? So the drought, we've had pretty unrelenting 20 years or so of drought, but they've been punctuated by these very wet years, like 2011, 2017, now 2013. We're tending to not get many wet years in a row, and that's hard to manage for. So things like Great Salt Lake, where we're losing some of that resiliency, and we haven't had conditions where we've had wet year after wet year after wet year. That just has not been in the cards for us since about the year 2000. We've had some very dry years, and again, really wet years. I think of this as, and Rob mentioned this, as increasing climate variability, where this is shown on an annual scale, but within this we can have really wet winters sometimes. Those are hard, again, for reservoir operators to manage to try to reduce flood risk. And then we're going into these generally longer, drier summers. So we really need our water supply for people and for ecosystems like Great Salt Lake. Okay, let's see if we can make this work. This meme has shown up. Is it going? Oh no. Oh well. I think we get the idea of it. So this meme has shown up. It's run across my desk like 5 times in the last 2 weeks. So I said, okay, that's a sign, and I put it in my talk. So what we want to do, we want to keep our eye on the ball. We don't want to let one wet year really distract us and derail us, but we also want to get not so myopic on any one year that we keep the big picture in mind. And it's a great clip. You guys should Google it. Keep your eye on the ball. If it hasn't crossed your desk too. All right. So now we're coming back to this, some of the work that forestry, fire, and state lands have done, and they've done a great job of showing the lake elevations that are healthy for us. So we already know, without changes from the legislature, we already know the lake levels that we need to be at. We want to be in this optimal range in the white, in the middle there, but we're down in the red. So we know that we need to increase the lake level. So now I'm going to talk some ways as a hydrologist would think about how we might get there. So I'm going to talk some about water conservation and banking and water shepherding. And one important thing to think about is that all of these need to happen in tandem. And by the way, I'm not trying to include every potential strategy in this talk. I'm talking just about a couple of them. So just keep that in mind. This isn't meant to be every single, promising strategy that we can include. But for things like conservation, with the ag optimization program, farmers have been working really hard to conserve water. There's more money being put into that this year. We hope it will, conserve a lot of water for the state. But that's not the end, because if that was the end, then other water users can pick up that water and it never actually gets to the lake. So one way to incentivize conservation is through water banking or water marketing. And one reason I think it might be promising is because it does incentivize conservation. So it becomes more of a, don't necessarily only do this because it will help the lake, but it will keep you whole as farmers, or whoever can conserve water will try to keep you whole. So in this case, people would spend money to buy water, to purchase water from voluntary sales, from anyone who's willing to sell some of their water. And then that water would need to be shepherded down to the Great Salt Lake. We can't just, say some water's been conserved and it will magically get to Great Salt Lake, because we know that that's not the case. So all of these sorts of solutions have to go hand in hand. And that's challenging because there's no really one single bullet solution. We know that we have to enact a number of them all together. So with the Great Salt Lake Strike Team, we've ran some numbers. And again, this is from a very hydrologic approach. So we thought, okay, we're at 4189 feet right now. How much water would it take to increase the lake level? And this is pretty simple using the water balance that I showed you. The equation is here on the bottom. We know that we need to increase stream flow, groundwater precipitation times area. And then we have the lake bathymetry. So these are pretty easy calculations for us to come up with. And in these calculations, by the way, this is showing the total water that we do get already from stream flow and from precipitation. So I'll break this down a little bit more to just the conservation part in the next slide. And then we also need to ask, how fast do we want to go? How fast do we want to preserve the lake? And I think everyone would like to be there, like I said, one wet year, but we know that's not going to happen. Looking at numbers like this, it really shows this is probably a marathon. We need to be thinking about Great Salt Lake for many years or for decades. So you can see these numbers. I'm not going to read every one. So we have how much water to raise the lake in 5 years or 10 years and 20 years, and then how much to maintain Great Salt Lake at that level. And now let's separate the additional conservation we need to get to those numbers. Because like I said, some stream flow is already getting to the lake, some precipitation is already getting to the lake, some groundwater. So here we have some ranges, because we don't know if the next 5 years are going to be very wet or very dry. Probably Rob could help us narrow this down so we know what's coming a little bit more. And so we could say, to raise the lake to 4192 in 5 years, we might need anywhere from an extra 100,000 acre feet per year to 700,000 acre feet per year. And this helps us be able to plan. And again, this is not so much on the policy side, but purely as looking at the hydrology of the lake. So this is focused purely on increasing stream flow through conservation. And now I want to bring up a study that I did with an economist, Eric Edwards, a number of years ago, and we looked at water markets and how much they would cost. And so we wanted to looked at the marginal value of water. So how much water users pay for their water, or in the case of agriculture, the productivity, how much money they make from, say, like an acre foot of water. And then we could put this into models, and we wanted to say, if we wanted to bring water down to Great Salt Lake, how much money would it cost? So the first thing we did is say, let's assume that the state or federal government were to mandate curtailments. They were to say everybody has to conserve. This is showing 11% or 20% or 29% of their water. We did a bit of a sensitivity analysis. Looking at that darkest gray bar in each figure, that's assuming that there was no water markets, that the government just said, we're going to mandate water conservation, or we're going to curtail water by some percentage. And then we said, what if we added markets? So some people could conserve water more easily. Some people wouldn't want to conserve any water, and that would be their prerogative. And we noticed that the cost came down a good deal for the same amount of water. So this is one of the reasons that I like, or I think water trading might be promising along with conservation and water shepherding. Just to be clear of what's shown in this water, this is costs of water for urban users or reductions in profits for farmers. It's not the cost of implementing programs or kind of maintaining these sorts of programs. But we can see that this might be a pretty promising strategy, because when we think about places like Mono Lake, as Kevin mentioned, so far the city of LA has spent over $2 billion, and it's estimated to be more like $3.5 billion to mitigate dust in Owens Lake. That's not to restore a lake. That's not to have any of the benefits of the lake. That's just to prevent dust. All right, in this slide, I stole this idea from Jake Sarago. These are made up numbers, and the focus is on the idea. So the idea here is that we need to give up some things. We maybe can't have everything. So this is where hydrology ends and water policy and social analyses start and preference analyses type starting. But we can think about what do we want to have in the state? Do we want to have tons of urban growth, kind of unchecked urban growth? Do we want to maintain agriculture? And I think the answer to that is a resounding yes. Every survey I've seen, talking to farmers, talking to water managers, talking to everyday Utahns, everyone wants to keep agriculture in the state. It's just a matter of how we do it and to what extent. Thinking about mineral extraction and thinking about Great Salt Lake preservation. We know we need to get more to the Great Salt Lake, and so we need to think about which pieces do we keep. And by the way, I say that this is a part for policy, and that's true, but this is a place where science can help. It can lay out what our options are. So we can go into this with really our eyes wide open and understand our trade-offs. So my last slide here. So the big points, if you tuned out for the last 30 minutes or so, the big points that I want to make here are that first, consumptive uses are largely the decline of Great Salt Lake. And that's a good thing too, because we can change that. We know we need to deliver water to the Great Salt Lake. So not only conserve water, but deliver it to Great Salt Lake. We should leverage wet years. We don't want to let these wet years go by. That being said, we don't want to merely hope for wet years. Hope isn't a strategy. We can hope for them, but we should also be planning. And so to me, that means using these wet years and try to think about how much water can we get to Great Salt Lake in these types of years, because that's going to make conservation on the dry years that much easier. We're going to be able to ease up on the dry years if we really can maximize these sorts of wet years. And then keep it up. That's maybe a little slangy, but this is a long-term solution. When I think I'm a scientist, but if I were a legislator and trying to think about policies that we need to put in place that need to stay there for decades, that would make me probably stressed out. We all want that magic bullet of just do this, just sign this legislation and our problem will be solved. And I don't think we have that in Great Salt Lake. I think that those times have ended, and this is going to take many years of hard work. In this case, I've talked about water conservation, banking, and shepherding. They go hand in hand for Great Salt Lake. They're probably part of a portfolio. I just highlighted a couple potential solutions here. In our Great Salt Lake Strike Team policy assessment, we've outlined lots more solutions. So if you're listening to this and thinking, I hate the idea of water banking, that's great. Let's look for some other solutions too. And we've started to outline those. There's many state reports and other state agency reports, and they've done the same thing. So lots of ideas are out there. And then we know it's cheaper to preserve Great Salt Lake now than it is to try to restore it later. And last summer, we were really starting to hit these tipping points, and we know we don't want to go past them when it's going to cost us much, much more money. So with that, I'm not sure if we have time or, okay.